Hello, good morning. Hello. First of all, yes, this is Unit 2. Welcome to the Unit 2 office hours. I believe Don probably should have warned you that I would be here today and that the office hours had changed times to fit into my schedule here. So, good morning, Isao. I hope I'm saying your name correctly. Hello, Sulaiman. Hello, Ro. Hello, Canorio. So, good morning, everyone. At least it's morning where I am. Hello, Raydot. I hope you're all doing well this week. So, as I said, this is Unit 2, office hours for Unit 2. Don is otherwise engaged today and Wednesday. I will be here again on Wednesday. Normal service will be resumed next week in terms of times and instructor. My understanding from Don is that you have been working on the ML mini project and that you have completed up through question 3. Is that correct? So it's this information about nursing homes. All right, great. So yeah, we have this information about these nursing homes and these surveys. And, right. So brief review, right? We had information about providers. I had this simple state model. We wanted to predict fines based on the states. So you did this kind of group mean estimator. Whenever I teach Unit 2, yeah, I always say, well, question 1 is really more or less a pandas type question. We convert this data into a data frame, and then we use pandas methods. We do a group by and fit our data in that way. Question 2, so we wanted to classify, we wanted to try to predict. So I said, I want to try to predict which facilities are fine based on the business characteristics. So the simple features, this was numeric and Boolean features. You had to deal with the issue that you had some null values. Question 3, we were just looking at categorical features. You had to one-hot encode categorical features. We could have actually, I don't know how Don did this. This solution here, we had 2 pipelines, one here, at least in this solution that I wrote. The ownership here is a bit dense, not dense, kind of wide, I guess you could say. So I applied this truncated singular value decomposition. I don't know if Don did that in his solution. And then applied a random forest classifier. So my solution might be a bit different from the one that Don talked about. This isn't necessarily, the best solution. I probably would not have bothered actually doing this truncated SVD myself. But again, we're using a random forest classifier. So a classifier, we reach out as we are improving the score of the model. I see. All right. And all right, so question 4, we basically want to combine these simple features, these numeric and Boolean features. Oh yeah, sorry. Apologies for not introducing myself. My name is Russ, R-U-S-S. I'm joining you from Maryland in the US. And sorry for not introducing myself. I'm still a little bit asleep this morning, I think. Still waking up. Not had enough coffee. So question 4, we wanted to combine these simple features, these numeric and Boolean features that we have imputed, missing values, and the categorical features in a feature union. So remember, the feature union is a way, well, I take, one feature matrix and another feature matrix, and we just concatenate them together side by side. And that's what we want to do here. We have one feature matrix and another feature matrix, and we just want to concatenate these feature matrices together. So this business features, we could say here, for example, business features fit transform my data here, data right, and this is what the first couple of rows from our feature matrix look like. So do chime in if you have any questions here on any of what I'm talking about. Why Don sounds a bit different? That's because I'm not Don this morning. I'm filling in for Don. Are we expected to study everything in the Introduction to Algorithm textbook for Unit 1? Joaquin, well, this is not the office hour for Unit 1. But no. So once again, this is the office hour for Unit 2. So I'm filling in for Don. This is Unit 2's office hour. If you're here for Unit 1, that will be later today. But yeah, here's our feature union, as we said, our result for concatenating together these two models, these simple features and the categorical features. And, we're still looking to do classification. Right, that's not changed. We're just using a bigger feature matrix. So we could just try, first of all, if we try our random forest classifier, or FC. So random forest classifier. I was using a number of estimators is 200. Min samples leaf. I think before in my solution I was using 100. Random states is 0. We could try this and see what kind of results we get first. So we'll fit our model here. We had our positive probability method, so we pass this to the grader. Well, I mean, all right. Our score is, good enough. This is, remember, our accuracy score, right? Basically, all right, our grader is comparing the accuracy score we're getting with the accuracy score of the model solution. I think as Don said, right, we can possibly score better than 1. There's some suggestions up above right here. It says you may want to optimize the hyperparameters of your estimator using cross-validation, or try engineering new features. For example, see polynomial features. Have you guys talked about polynomial features before? As I said, have you talked about the polynomial features method in scikit-learn? Suleiman asked the question, all right, what informed the choice of random forest? Is it because we have a combination of numerical and categorical variables? I mean, you could use other classifiers. Frankly, I tend to go, so, all right, let's back up a bit. What are possible classifiers that you could use that you have talked about? Where is my, let's see if I could find, hang on. So, right, what classifiers have you seen or talked about or are aware of? Right, this is, apologies, should have loaded up my whiteboard. So logistic regression, decision tree classifiers. Come on. I don't know why this website seems to be going so slow today, but create new board. We're getting there. So, all right. So, as I said, so logistic regression. You mentioned a decision tree classifier. Classifier, and you mentioned random forest. And k-neighbor, yep, so there's a k-neighbor classifier. So k-neighbor. Can anybody tell me some good and bad things about any of these classifiers? Like what's good about logistic regression, or what's bad about logistic regression? I mean, one thing that's good about logistic regression is that generally it's kind of fast to fit. I mean, this will slow down somewhat as you get more features and more data. This is a regularized model. Yeah, logistic regression is easy to implement. It's been around for, a number of years. Quite a number of years. It's a little bit restrictive, right? What do you want to separate? What is the idea of logistic regression? You want to separate the feature space into two parts. Feature space using a hyperplane. A hyperplane. Right, what do I mean by hyperplane? Well, in 2 dimensions, a hyperplane is just a line, right? I 2-dimensional space. I'm looking for some sort of line where everything on one side of this line is in one class and everything on the other side is in another class. I'm just thinking about a classification problem with 2 classes. So logistic regression, you're looking to separate the feature space into 2 parts using a hyperplane. In 3-dimensional space, a hyperplane is just a regular plane, right? A 2-dimensional piece of paper, right? And everything on one side is in one class and everything on the other side is in another class. So it's sometimes logistic regression is not able to divide the space into 2 parts very well. So it can be a little bit limiting to work with logistic regression. It's simple, it's kind of easy to understand what's going on, but it can be a little bit limiting. Let me address William's question here. He's saying you want like a fresh copy of your notebooks. don't probably mention this, but if you go to your pod and you open up a terminal window, so new terminal, and you have a terminal window, if you say cd for change directory to data course, there's a script called update modules. Let's make this a bit larger here. Right, there's a script called update modules. You could run the update modules script. How do you run it? You do this by typing a period and a / and then update modules.sh. And then you can type in machine learning with a hyphen. So update modules, so period / update modules.sh machine-learning. And this will download the material into a directory called machine-learning.new. And so you'll have a fresh copy of all of the notebooks, including the mini projects. So if I go here, machine learning new, this is a fresh, clean copy of all the notebooks, including the mini projects. Beware, however, if you run this update scripts again, it will overwrite this machine learning.new directory. So, once you do this, you may want to rename this directory so that if you have to do this again, you won't overwrite things that you have already. All right, so it's the update modules script, which will allow you to get new versions of the notebooks. So just regression is good. It's fast, generally easy to fit. It's a regularized model, so there's some feature selection going on. But it can be a little bit limiting by the fact that we are trying to separate the feature space using a hyperplane. Decision tree classifier, well, it works differently, right? You're basically the predict method, right? You're asking a question. Oh, here's this feature. Is this feature less than or equal to this value, or is it larger than this value, right? And you ask this series of questions, and you get this tree, this branching tree. Again, a decision tree classifier is easy to understand how it works in action. So this is easy. Again, a decision tree classifier is easy to understand what it's doing. The problem with a decision tree classifier is that it may need to be very deep in order to give us good results. Right, so this basically generally needs to be deep for good results. If I could spell results. Right, so I need to have like a big tree, very deep tree, in order to get good results with a single decision tree. Now, a random forest classifier is a collection of decision trees. Right, and how do we build these decision trees? Why is a random forest not just copies of the same decision tree? What makes each decision tree in a random forest different? Can anybody tell me that? right? A random forest is not just a bunch of copies of the same decision tree, because when the random forest is fit, you fit on different subsets of the training data, and you fit on different subsets of features of the training data. You know, if I have 10,000 rows of data in my feature matrix, you know, the random forest, I might say, well, take the first 2,000 rows, or take some random collection of 2,000 rows, fit a decision tree on that data. Oh, take a different random collection of 2,000 rows, fit a different decision tree on that data. But it's also could be using different subsets of features to fit these decision trees. So we have a whole collection of decision trees which have been fit on different data and different features. The idea of a random forest classifier is we want to get good predictions. I mean, of course, this is ideally our goal for every machine learning model. We want to get good predictions, but the idea of a random forest is we average away some of the variance. Right, you have talked about or heard about this bias-variance trade-off when you are building a machine learning model. This is the constant battle that we have to deal with when we're doing machine learning. I don't know how, I imagine Don has started talking about this, right? But when you're doing machine learning, we want to find the signal that's present between our features and our what we're trying to predict, our targets. We want to find the signal that's present between the features and the target we want to predict without picking up too much of the noise that's present in our training data. Right, and the noise, is generally referred to as the variance. Right, our model generally suffers by this variance. Right, there's error due to the fact that we have trained on a noisy subset of data, and that's the variance. The general idea of a random forest classifier is that each individual decision tree could suffer from its own variance problems, but the idea is we train a collection of decision trees. We basically average the results. In this case, we'd average the probabilities of belonging to classes. And the hope, we can never quite guarantee this, but the hope is that we will average away some of the variance of the individual trees. And the k-neighbors classifier is, kind of does what it says in the tin, right? You look at, I have a point in my feature space, and I look at the neighbors that are closest to it, and you do some kind of voting or averaging procedure using these neighbors to classify this new point. Now, Suleiman asked the question, what informed the choice? Is it because we have a combination of numerical categorical variables? Well, actually, any of these models right here could work if you have a collection of numeric and categorical variables. You could use any of these models, right? Because you do a one-hot encoding to change your categorical variables into numeric. So any of these models could be a choice for this classification problem. What was the choice? Well, logistic regression is fast, but it's a little bit limiting because you're using this hyperplane to select features. Sorry, to make predictions. So it's a little bit limiting. A decision tree needs to be deep for good results. I tend to go for random forest classifiers because of the good properties. You can fit a different kind of boundary. You're not just trying to separate the feature space using a hyperplane. You can have a more complicated boundary. And because of this, averaging away the variance kind of idea. So I might use logistic regression as a starting point, as a kind of baseline model, but I tend to go for like the more complicated models because, well, I tend to get better results. But again, there's a trade-off. Logistic regression is kind of easier to explain to someone. It's easier to explain where the predictions are coming from. The same way a decision tree, I could draw a decision tree and I could tell you exactly where the prediction is coming from, right? You just kind of go through the tree and you could see where the decisions are coming from. A random forest classifier, it's a bit more difficult to see where the results are coming from because it's this average of the of the individual decision trees. So there's this trade-off between the explicability of the model and the results of the model. So we have to sometimes think about, what do I need from my model? Do I need to be able to explain the results to someone else very clearly? If I need to explain the results, I might go for these somewhat simpler models because then I could explain where the results are coming from. If I want better results, I will tend to go for a random forest classifier. I might try a k-neighbor classifier as well. K-neighbor classifier, for it to work well, I ideally have a collection of data that kind of covers the feature space rather well. Now, Mickey asked, could you explain how to use the random forest to get the relevant features for our model? Yes. So if we look at the documentation, remember, always go and look at the documentation. So I can look at random forest classifier. I always suggest to students, well, it's valuable to read through the scikit-learn documentation. There's a lot of stuff in there which will, which we may not have time to talk about in this course. So random forest classifier, if we scroll here down to the attributes, we find here something called feature importances. Feature importances. They say the impurity-based feature importances. we could look at this in our results. So if we go back here to our business model, so let's make some space here. So we have our business model, which is our pipeline. Remember, a pipeline has a named steps attribute, which is a dictionary. I could get the random forest classifier by using the name that I have given it in this tuple. Remember, right, these names in these tuples become the keys in the dictionary for the name steps. So this is my random forest classifier, and this has a feature importances with an underscore at the end. This has a feature importances NumPy array. The sum of these elements should be 1. So this is a NumPy array where of non-negative numbers whose sum is 1. And the idea here is, well, the larger numbers are pointing towards the more important features. So it looks like, in fact, this first feature right here has the largest feature importance. It looks like this feature here has the second. Remember, right, I could do an arg sort. And let's do, I think I want to say ascending is false. NumPy, oops, arg sort. Ascending. Let's do reverse. Reverse, inverse, ascending, descending. Oh, come on. All right, I obviously can't quite remember the parameters, but the idea here is, well, this feature at the end is the largest feature, right? The largest value. This is the next largest value. Remember, argsort gives us a index of arrays. So this is saying the wanted indices 4 and 6 are the smallest numbers. So, right, 0 and 0. And then index 11 is the next smallest, and so on. So, right, so this feature right here, feature 0, is the largest feature importance. So that one, you know, again, you might say, well, that's the most important feature in terms of the predictive power of our features. Now, of course, we'd have to trace back through where is feature 0 coming from. Well, feature 0 is going to be coming from our simple features model. So I need to go, you know, look back through the simple features and, you know, see where this feature is coming from. So this is where it gets a little bit, you know, complicated. Where's my simple features? Right, it's this bed search column. Because we have the column select transformer, and the first column is this bed search. I use the keyboard shortcut, either the letter A or the letter B. So if I select this cell here, and I'm in the command mode by the blue bar, if I hit the letter A, I will insert a new cell above where I was. If I hit the letter B, I insert a new cell below where I was. So, right, but it's the feature importances which can allow us to look at which features are most relevant. But again, I'd have to start tracing back through where these features are coming from. Right, so features with indices 0 and 1 are the most important. Feature 7, 0, or with index 7, 0, 1, 2, 3, 4, 5, 6, 7. Where is this coming from? Is this coming from my simple features or from my categorical features? Right, 0, 1, 2, 3, 4, 5, 6. 7 right here. And of course, things get even more complicated if, like in this categorical features, I'm doing this truncated SVD. Then, right, truncated SVD, it's this feature selection kind of process. Right, and these new features that you get out of truncated SVD are combinations of the original features. So hopefully I've given you some kind of answers to your questions here. We had a score of 0.956. That's a score from the grader. Remember, of course, we could look at the score from the model itself. If I look at business model score data and find counts, find counts greater than 0. Right, what does the score function here do? Remember, this score function right here is an accuracy score. Our classifier, our estimator is a classifier. Remember, what does score do right here? Well, it takes predictions using this input data, compares those to the real labels. Remember, the real labels are trues and falses. So remember, this right here is an accuracy score of the classifier. 69% accuracy, not bad. We could try and improve both the grader score and the accuracy score by engineering some features. A suggestion is polynomial features. What does polynomial features do? Is it says, well, it generates polynomial and interaction features. So generate a new feature matrix consisting of all polynomial combinations of the features with degree less than or equal to the specified degree. So, for example, always good to look at their example. If the sample input is two-dimensional and has two variables, two columns A and B, the degree 2 polynomial features, well, they give us a column of 1s, they give us a column of A and B. They give us 3 new columns in addition, well, 4, but one of them is 1s. They give us 3 additional columns here, which are the most relevant ones. They look at the squares of the value A, the squares of the value B, and these so-called interaction terms, A times B. Right, so you're generating new features in your feature matrix. And this is what we could try here. We could try this polynomial features method. So from sklearn pre-processing, we could import polynomial features. We could add this into our pipeline right here. So we take our features and then we want to generate new polynomial features. So we could add a new step here, say I want to generate polynomial features. We'll go with the default value of 2. This is the degree. Right, the important parameter, most important parameter is degree 2. I'm going to turn this include a bias parameter which is true by default to false. Why? Because this isn't useful if I'm doing a random forest classifier. The include the bias is referring to this column of all ones. Right, include bias if true, by default, include a bias column, the feature in which all polynomial powers are 0, i.e. a column of 1s. That's not going to be useful if I'm doing a random forest classifier. I would argue this default should be false, but that's for another day. So I'm going to say include bias is false. So I take my features, I generate all these polynomial features, and then I run them through my classifier. It will take longer to fit, because now I have more features. My greater score increases a bit. What is the score of my model, the accuracy score? Well, it was 69%. All right, it was 69, like 0.1. It goes up to 69.2. My accuracy gets slightly better. What I probably might need to do is I might need to tune hyperparameters in my random forest classifier. I might, if I remember correctly, my problem was a little bit unbalanced, I think. I might say, let's make the class weight balanced. We could go for another fit again. My greater score improves a bit. Well, how does my accuracy score? My accuracy score actually decreases, but this is because we're balancing the classes, you know, more, right? So my fine counts greater than 0. Value counts. Let's try that. Right, I have twice as many falses as trues. So my class, you know, the false class is like twice as large as the true class. I might need to do some grid searching right here on something like min samples leaf or max depth or min sample split or something of this form, right? I could say from sklearn model selection import grid search CV. I might stick in a grid search CV here on my random forest classifier. Let's put the min samples leaf into my parameters. Right, param grid dictionary min samples leaf. I had 100, let's try 300 and 500. CV is 5. Of course, now my, alright, so let's see, let's get my parentheses in the right place. Of course, now my fit method takes longer because, you know, it's checking 3 different values for min samples leaf and doing 5 models for each. So there's 15 models that need to be generated. So this is, you know, this is a time when I say, oh, I want to fit a model. All right, I'll start my fit. I wander off. I get myself another coffee. I chat with my wife. Whatever. Go check the mail, depending upon what time of day it is, you know, etc. I come back when my fit is done. Sitting here watching a model being fit isn't the most exciting thing in the world. My grader score, well, still 1.039. My accuracy score, well, all right, hasn't changed. I might need to do grid searching on other parameters on my random forest classifier. Or indeed, I might wrap my grid search around the whole pipeline. Remember, I could do grid search on something in one of the transformers. I might add in another step here after polynomial features, right? We've generated a bunch of features. Well, I might add in a step to do truncated SVD. After the polynomial features, reduce the number of features back down again. Of course, one of the problems or possible problems of doing polynomial features is that my feature, oh, sorry, this is best estimator, and then feature importances. Right, doing polynomial features, the number of features has grown a lot. My feature importance is it's still a NumPy array whose sum is 1, but now it becomes more difficult to kind of argue a bit about my feature importances, right? Feature 84 is the most important one. Feature 84 is going to be some sort of combination of one of these polynomial features. I mean, I think there's a way that I could work this out. Right, but I'd have to reread the documentation here, right, to figure out, to try and figure out what sort of combination of my features are giving me this most important feature. Right, it becomes even more complicated to try and work out what this combination of features is. I mean, I could try and do it, but it will take me some time because, again, this is going to give me some combination of two of my features, because this is coming from the polynomial features. I'm sorry, of course, this is the most important one, not 84, 33, because the arc sort, I want the largest feature. I still have 0 here, but towards the top, but you know, again, I have these combinations which are a bit larger. So any questions on what I've done here at the moment? Right, you know, I want to try and emphasize, right, the more important things, right? It's, you know, all right, yeah, you get your score from the grader, but, you know, what is this model actually doing? You know, what is polynomial features doing? What is the random forest classifier doing? It's a collection of decision trees. The idea is, well, we still want good predictions, but the idea of a random forest is that it washes out some of the variance that might otherwise be present in the individual decision trees in the model. Again, if I wanted to try and prove my accuracy right here, well, I might need to do a grid search on more than just a min samples leaf. I might want to look at the max depth. Again, as I said, I might want to put my whole pipeline inside grid search and, in fact, change the degree of polynomial features. I might want to add in a step after polynomial features here for truncated SVD. So random forest fits every node in the decision tree. Well, remember, a random forest is a collection of decision trees. I don't know what you mean by fits every node. You know, a decision tree will continue fitting until, right, some limit might be achieved on its hyperparameters. You know, if we're looking at min samples leaf, and min samples leaf was 500, right, this basically means that if you get to a node that, and if you wanted to split, and it would create nodes which are going to be smaller than 500 rows, it won't do that split. Right, but so a random forest is a collection of decision trees. Each decision tree can be fitted on a different subset of data and a different subset of features. So we have different decision trees. And the random forest kind of averages over this collection of decision trees to get a prediction for the data. So think about this some more. I'm out of time. I have to go get prepared for a meeting with another group of students. Think about this and bring your questions to Don. Thanks for your questions. I will see you all again on Wednesday. Don will be here tomorrow for your office hour. I will be back on Wednesday. Don will be on Thursday, and next week we'll resume normal schedules with Don. So I will see you on Wednesday, but again, Don will be with you guys tomorrow as normal. So have a good day, and I will see you soon.